Hello guys, and welcome to another calculus video. In this video, this is part 3 of the infinite summation guide. We're talking about special cases and tricks here, so a lot of higher level tricks and manipulations that you can do rather than just base level stuff and, formulas to remember. Um, and also just, special cases of certain integrals that we're going to be using. So in this section of the video, we're going to be talking about converting infinite products to infinite summations, which can give us some very nice formulas for summations, using integrals to solve summations, the partial sum trick, which I think you guys will find very interesting, polylogarithms, changing the order of summation, and special summation functions. So first of all, we're going to talk about infinite products. So there's a very interesting connection between infinite products and summations, and that is, if you take the natural log of an infinite product of an, it becomes the sum of the natural log of the terms an, because ln of ab equals ln a plus ln b. So if we take the natural log of a huge product, it becomes a sum of the natural log of all the factors. So typically, this is how we would evaluate an infinite product. So if you get an infinite product, the first thing you should be thinking about doing is taking the natural log and then converting it into a summation. However, there are a few situations where we can derive infinite summations from products that are well known. So most often, and this is pretty much the only one that really comes up in many situations, is the product representation of sine of x. So sine of pi x over pi x is the same as the product from n equals 1 to infinity of 1 minus x squared over n squared. So taking the natural log on both sides, we get that the sum from n equals 1 to infinity of natural log of 1 minus x squared over n squared equals natural log of sine of pi x over pi x. So that's something always to keep in mind. Since infinite product representations are few and far between, this method is not altogether too useful. However, the formula for sinc x does show up in many summations. So just remembering this formula is probably a good idea. And if you're ever, given some infinite product, you can always try and turn that into a summation identity. Next up is polylogarithms. So these are a type of special function that is defined by an infinite summation. So many infinite series can be expressed in terms of polylogarithms. Sadly, very few values of the polylogarithms for s greater than 2 are expressible in terms of standard constants. So what that means is if you see some summation that can be expressed as a polylogarithm, chances are there's no way to express it in terms of standard constants like pi, e, and gamma and stuff like that. And the best way to write that, to represent that summation, is just using the polylogarithm. So the polylogarithm is Li. It has two variables here, s, which denotes the sort of the order, and z, which is of course the input. And this is the sum from n equals 1 to infinity of z to the n over n to the s. So notice we could say that Li 0 of z is just 1 over 1 minus z, and Li 1 of z is just negative natural log of 1 minus z. Also, to find the order of to increase the order by 1 of a polylogarithm, all you have to do is divide by x and then integrate from 0 to z, and then integrate with respect to x, of course. Some polylogarithms do have functional identities which allow us to evaluate them at certain values. For example, the dilogarithm, which is Li sub 2, of the golden ratio is actually calculable, or maybe it's 1 over the golden ratio, I'm not certain, but there are some very interesting identities with that. So know that most values of the polylogarithm are not calculable, but some certain specific ones are. Now, my favorite trick right here is the partial sum trick. It's a trick that I use very often. I've not really seen many people use it, but I guess it's just because they use it in a different way. And it's used when dealing with complicated summations with multiple different terms, and maybe you can't use the same method for every single term in there, so that means you're going to need to use this trick instead. Its purpose is to get around the rules which prevent us from separating summations with diverge. So, for example, if we have sum from n equals 1 to infinity of f of n minus g of n, and we can easily calculate both of these summations, but it's not going to be equal to the summation from n equals 1 to infinity of f of n minus g of n if one of these diverges or if both of them diverge. Or I guess both of them would have to diverge. So what we do instead is we know that the sum from n equals 1 to infinity is of f of n minus g of n is the same as the limit as m goes to infinity of the sum from n equals 1 to m of f of n minus g of n. However, now we can actually split these summations because when we're taking the limit as m goes to infinity and we put the m as the upper bound here, technically m is always going to be a finite number, right? We just end up taking the limit as m goes to infinity afterwards. It's the same thing, when you're taking a limit as x goes to a 0, you know that x is not actually going to be equal to 0, the same way that we could say that m isn't actually infinite, but we can just take a limit. And in this case, if this limit exists, which in most cases it is as long as the integral converges, or the summation converges, then we can actually split the summations in two. The only difficult part is now, rather than calculating an infinite summation of f of n and g of n, we actually have to calculate the partial sum. So if we can calculate the partial sum up to an arbitrary upper bound for both functions, we can add and subtract them and take the limit as the upper bound. In this case, m goes to infinity. And it's the same thing as taking the limit of the partial sum of the original summation. So it's the same thing as taking limit as m goes to infinity of sum from n equals 1 to m of f of n minus g of n. So let me show you how this works. So some functions telescope very nicely, which allows us to easily take a partial sum, even if those extra terms at the end diverge. So remember, in the last video, we talked about how those extra terms at the end can sometimes be a little bit nasty to deal with. And so, if you have a series where those extra terms actually go to infinity, then you can use this method in order to still separate the summation and use telescoping series, even though those terms at the end go to infinity. So, and for some other functions, they just have a very easy partial sum formula, and so taking the limit of the partial sums is much more straightforward than attempting to evaluate the summation by any other method. So, let's look at an example here. This looks really, really gnarly. We have ln 2n squared plus 5n plus 3 over 2n squared plus 5n plus 2. Now, this is equal to s, and actually we can go ahead and factor this into 2n plus 3 times n plus 1 on the top and 2n plus 1 times n plus 2 on the bottom. And when we go ahead and factor this, this allows us to split it up into multiple different summations. And notice that this summation right here is telescoping, and this summation right here is also telescoping if we separate these. However, we can't actually separate this into two separate summations without using the partial sum trick, because if you look at these natural logs, if we have telescoping natural logs, the end result is going to be natural log 2n plus 3, limit as n goes to infinity, which is just infinity. So both of these summations would diverge, which is why instead we're going to calculate the partial sum. So for example, the partial sum from n equals 0 to m of 2n plus 3 minus ln 2n plus 1 is just ln 2m plus 3 by telescoping series. And you can go ahead and write out the terms and cancel everything out, and you'll find that this is true. Similarly, for negative ln n plus 2 plus ln n plus 1, it just becomes negative ln m plus 2. Again, just write out those terms and cancel everything out. So our overall sum, s, is going to be the limit as m goes to infinity of s1 plus s2. This is s1 and this is s2. And s1 and s2 were both dependent on m. So this is the limit as m goes to infinity of natural log of 2m plus 3, this one right here, over to minus natural log of ln m plus 2, which is the same as putting m plus 2 in the bottom, which is just ln 2. So some other functions have some neat partial sums without being telescoping series. So some examples here, really common right here, sum from n equals 1 to m of natural log of n is equal to natural log of m factorial, which is really helpful. Sum from n equals 1 to m of 1 is just m, of course. Sum from n equals 1 to m of natural log of 2n plus 1 is natural log of 2m plus 1 double factorial. Sum from n equals 1 to m of b to the n equals 1 minus b to the m plus 1 over 1 minus b. And this actually holds up even if b is not less than, or if the absolute value of b is not less than 1. So you could use b equals 2 in this situation, though I don't think there's many summations where you'd have to actually calculate this. Also, for all powers n to some power k, there is a polynomial formula for the partial sum right here, so I just have the one for n right here. So sum from n equals 1 to m is m times m plus 1 over 2. And this one for sine, you probably won't see this showing up, but these sums are pretty easy to calculate in general. So now let's go on to the next method, using integrals to evaluate summations. So we can interchange integrals and sums given as long as, of course, this is again Fubini's theorem, which we have talked about several times in the past. What we need is that if we have some function fn of x, which is dependent on n and x, and we're summing it from n equals 1 to infinity, and we're integrating it afterwards. In order to interchange that sum and that integral, we need the absolute value of f. If we replace fn with its absolute value, it still needs to converge. Also, you can also have it the other way around, because if this is less than infinity, then these two will be the same anyway. There are also many cases in which we can interchange the integral sign and the summation sign, even if this condition isn't satisfied, using what's called the dominated convergence theorem. So, in general, we're going to be able to make this switch whether or not this condition is satisfied, but it's always good to check just to be sure that you're not doing anything that you'll regret later when you found out that your sum actually wasn't equivalent and you just wasted a ton of time. Note that interchanging an integral and a sum is the same thing as applying Feynman's trick on a summation. So both of these tools are really the same tool. It's just doing steps in a different order and steps that you're allowed to exchange the order of. And both of them are very, very useful in evaluating a variety of summations. So let's look at some examples. So this is a very classic one. Sum from n equals 1 to infinity of sine squared of n over n squared equals 1/2 times the sum from n equals 1 to infinity of 1 minus cosine 2n over n squared. But you'll notice that 1 minus cosine 2n over n is the same thing as the integral from 0 to 2 of sine of nv dv. You can go ahead and check that for yourself. This is a really, really, really helpful formula in a lot of different situations. So when we go ahead and substitute this in, we go ahead and interchange the integral and the sum, and we get that 1 over v, the integral from 0 to 2 of 1 over v times the sum from n equals 1 to infinity of sine of nv over n dv. Once you go ahead and work through all that math, this ends up being some inverse tangent function, I believe, inverse tangent of cotangent of x over 2, which becomes pi over 2 minus x over 2, or v over 2, sorry. And then you go ahead and integrate, and you get the answer being pi over 2 minus 1/2. So commonly used tricks right here. If you have some polynomial of n times natural log of 1 plus 1 over n squared, or something similar to that, usually when you have this polynomial of n times natural log of 1 plus 1 over n squared, there will also be some other polynomial of n subtracting it. So for example, natural log 1 plus 1 over n squared times p of n minus some other polynomial q of n. So what we'll do in this situation is we'll get s of x equals sum from n equals 1 to infinity of p of n times the natural log of 1 plus x squared over n squared. Then when we differentiate with respect to x, we end up with this nice thing which can be evaluated using rational summations. And again, there would also be some q of n over here, so this p of n could be of a different order. So that's a really, really useful trick because rational summations are something we covered in previous videos, and they're relatively easy to calculate. They just sort of have a general formula that you can use for anyone. And so in turning a natural log into a rational summation is a really cool trick. So the strategy for knowing when and how to use this method is very, very tricky and nuanced, but the ideas remain the same as when using Feynman's trick in integration. So I have a video on that if you guys want to watch that. And so the idea behind trying to pick when we're gonna apply this trick is the exact same thing as when we're using Feynman's trick in integration. So for example, if we have some f of a n minus f of b n, we're going to rewrite this as the integral from b to a of f prime of nv times n. And similarly, if we have some natural log a plus b g of n, we're going to differentiate with respect to a, and we're going to get f of n over a plus b g of n, which is hopefully a little bit easier. Obviously, it depends on the situation. So the two most common uses in summation are when we have f of a n minus b n, or when there is a natural logarithm involved. But as always, keep your eyes peeled for lots of situations where this method is useful because it can turn seemingly impossible summations into easy ones. So now let's talk about an even more powerful trick, changing of the order of summation. So let's say we have some double summation. On the inside, it's the sum from m equals 1 to infinity, and on the outside, it's n equals 1 to infinity. Now we can change the order of summation from summing m first and then n to summing n first and then m whenever the sum of the absolute value of a and m is less than infinity. So if you just replace whatever your summand is with the absolute value of it and it still converges, then you're all good, and you can go ahead and switch the order. Again, there are many cases where you can do this without satisfying this criteria, but in general, it's good to just give it a little check. So we're only going to change the order of summation when we're dealing with a function that's defined by a summation. For example, the harmonic numbers h sub n equals the sum from k equals 1 to n of 1 over k. We have zeta of s equals the sum from n equals 1 to infinity of 1 over n to the s. Eta of s equals the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n to the s. Sorry, I guess I messed that up. And also the polylogarithms here that we talked about early in the video. There we go. So, whenever we have one of these functions in our summand, we can go ahead and substitute in this definition, and then it becomes a double summation. Then we can interchange the order, and hopefully it makes it a little bit easier to evaluate. So when dealing with these functions, it's sometimes easier to evaluate the summation in the opposite order. So look, we have this sum from n equals 1 to infinity of zeta of 2n times 4 to the negative n. Now, the first thing we're going to do is we're going to replace zeta of 2n with the sum from k equals 1 to infinity of 1 over k to the 2n, which is just the definition of it right here. And so now we have this nice double summation. Now what we're going to do is we're going to flip the order of summation. Now notice that this is entirely positive, so this is totally justified in this situation. So now we're going to sum over k on the outside, and we're going to sum over n first. And notice that we can reorganize the summand into 1 over 4k squared raised to the n power. And we're summing from n equals 1 to infinity, so that means we're going to end up with the sum from k equals 1 to infinity of 1 over 4k squared over 1 minus 1 over 4k squared. Reorganizing, we get the sum from k equals 1 to infinity of 1 over 4k squared minus 1, or 1/2 times the sum from k equals 1 to infinity of 1 over 2k minus 1 minus 1 over 2k plus 1, which is just a telescoping series which evaluates to 1/2. So notice how we took this absolutely gnarly zeta function multiplied by power, and just by substituting in the definition and exchanging the order of summation, we ended up with a nice little rational summation, which is something that we totally know how to evaluate. So that's generally how most of these problems are going to go. However, sometimes it does get a little bit hairy. So sometimes we have what I like to call complex bounds, and what I mean by complex bounds is the bounds aren't n goes from 1 to infinity and k goes from 1 to infinity or something like that. It's rather, on the inside we have k goes from 1 to n, and then n goes from 1 to infinity. And so this is a little bit more difficult because changing the bounds is not always the easiest thing in the world. Now, you could memorize formulas for how to change the bounds, and that's perfectly okay. But I find it's easiest to visualize the bounds change in order to actually understand what you're doing when you're changing the bounds and changing the order of summation. So, it can be very tricky to do this because the bounds on the inside depend on the outside variable, but there is an easy way to figure this out. So it's really a three-step process that I'll go through in depth with you. First, you're going to draw the discrete graph of the summation region, and I'll show you what that looks like. Step 2, you're going to determine the overall region for the new outer variable. So the inner variable, you're going to switch to the outer variable, so you're going to determine the overall region of all the values that this variable can take on. And then step 3, you're going to determine how the inner variable's bounds depend on the outer variable. So let's look at an example, because that doesn't really make any sense, right? So an example here is, in general, when we have complex bounds, we're talking about harmonic numbers. So the sum from n equals 1 to infinity of h sub n over 2 to the n. So we're going to substitute in the definition of the harmonic numbers, and we get the sum from n equals 1 to infinity of the sum from k equals 1 to n of 2 to the negative n over k. Now we want to switch the summation here. So let's go ahead and visualize it. N takes on all values from 1 to infinity. K takes on all values from 1 to n, which means that k is always going to be less than or equal to n. So what we're going to do is we're going to draw the discrete graph here. So I marked a point 1 and 1 right here, and this is our n axis and this is our k axis. So this is just a visualization of all the possible values that n and k can take on. For example, this point right here would be 1, 1. This point would be 2, 1, essentially meaning that n equals 2 and k equals 1. And then this would be 2, 2. This would be 3, 1, and so on and so forth. You guys know how coordinates grids work. So I just filled in every single possible point. Now, how did I do this? Well, first of all, I know n takes on all values from 1 to infinity, so I don't really need to worry about that. What I am worried about is k. So first of all, I drew the line x equals k in the graph right here. So this is our important dependence right here. This is how the bounds of k depend on n. So I filled in all the points on this line, and then I realized, okay, well I know that k goes from 1 to n. So that means k is going to take on all values from 1 to n. So for any given n, we're going to have k going from 1 to n. So I know I just repeated myself there, but I don't really know a better way to explain it. I'm just going to have k taking on this value, taking on these two values up to n, taking on these two values up to n, again, or these three values up to n. And so when we switch the bounds, now k is going to be on the outside, correct? So first of all, what are all the possible values that k can take on? Well, since n goes from 1 to infinity and k goes from 1 to n, that means k essentially is going to go from 1 to infinity. So that's easy. We already got our outer bound corrected. But now we need to figure out our inner bound, which is the difficult one. So notice if we look at our graph, let's pick a certain value of k. For example, let's pick k equals 2. Now when I pick k equals 2 and I look at this whole line, I notice that n takes on the value 2, which is this point right here, 3, 4, 5, 6, 7, right? All the way from 2 up to infinity. If I pick another value of k, say k equals 4 right here, I find n equals 4, 5, 6, 7, 8, 9, all the way up to infinity. So this is just exactly how this is going to work. For any value of k, n is going to take on that same value and then every value after that up to infinity. So notice, after just drawing this graph in this line, I was able to visually reason out what my bounds are going to look like. I didn't apply some magic formula or anything. I just drew it out and visualized what my summation is going to look like. So this tells us that n takes on all values from k to infinity, which is this other bound right here. And then after evaluating the inner summation here, it's just going to be 2 to the negative k over 1 minus 1 half. And then evaluating the outer summation using the natural log 1 minus x, we get that our final answer is natural log of 4. So that's a really, really cool trick that I think is probably not taught. I'm not really certain since I haven't taken the classes on this topic, but I really think that these sort of visualizations should really be more respected because it's a very, very powerful tool and it really helps me understand everything that I'm doing when I'm solving these problems. So most of the times the bounds will be simple and linear, for example, like from n equals 1 to k plus 2 or something like that. But be careful and check individual cases because it's super easy to make a mistake in this process. And if you change one bound, the whole value of your summation changes. So usually this is going to come up when calculating sums involving the harmonic series, but it could also show up in other situations. And the last topic in this video is special summation functions. So this is not something that I think is super important to learn, but basically mathematicians end up defining a lot of special functions which are defined by infinite series. And most of the time, this is a generalized solution to a differential equation. So these can be used to represent the results of summations when no other closed form exists. So what I mean by this is, for example, let's say you're a mathematician and you're studying some random differential equation that some physicist needs to solve. And you use power series to solve it, and you end up with some infinite series, but you realize that it actually can't be expressed in terms of any other known function, right? So it's just a new infinite series, which is the solution to this differential equation. So what you'd do is you'd slap your name on it, and for example, for me, I'd call it the dr3213 function, right? So that's pretty much what we end up doing in these situations. Now, it's not always named after the person who invented or discovered it, but in many cases it is. So I have a few examples here. The Lurch transcendent right here is a generalized version of the zeta and polylogarithm functions. So it's a function of z, s, and a all at once. And it's the sum from n equals 0 to infinity of z to the n over n plus a to the s. And you can see the relation to the polylogarithm here. The hypergeometric functions are solutions to some crazy differential equation. And this is just one class of hypergeometric functions, but it is the most common one. So it has a little subscript 2, and then an f, and then a subscript 1, and then it has 4 inputs, a, b, c, and z. and it ends up being the sum from n equals 0 to infinity of a sub n, b sub n, z to the n over c sub n factorial. And in this case, a sub n just means a times a plus 1 times a plus 2 all the way up to a plus n minus 1. And that means that a0 is just 1. And finally, we have the Bessel functions. So these are commonly used in physics, and they are also the solutions to different classes of differential equations. And I don't have the definitions in here because there's just so many different types of them, and they're all different, and they all have different orders and stuff like that. So these are very interesting functions. Sometimes they show up in integrals as well. So I'm not going to go over all the examples of generalized series formulas, but just know that sometimes if something shows up in Wolfram alpha, if you're plugging in a summation, it gives you an answer in terms of the Struve function or the generalized confluent hypergeometric function. Chances are that's just a generalized summation function that somebody created in order to better represent an answer to their summation. So that's it. It's time for some practice problems. Note that I've starred this one as an extra hard problem, so just be aware of that. And here are my 12 practice problems. I wasn't able to come up with too many for this video simply because these, so many summations that use these tricks are very similar to one another, and I didn't want it to get dry and boring. So here are 12 practice problems. Go ahead and give them a shot. If you want any help figuring these out, I'm happy to help anyone who wants to join my Discord. And yeah. So hopefully you guys were able to figure out all of these summations. I didn't have any super hard ones except this number 4 right here. If you want more problems, I'm always happy to look for some for you. And yeah, I hope you guys enjoyed this series and this video, and I hope you learned something and you're ready to evaluate any summation in your path. So thanks for watching. I hope to see you next time, and bye.